So, continuing our discussion on supersonic expansion and compression, we have seen that for isentropic compression the relationship is given by minus d theta equal to root over m square minus 1 d w by w, where w is the flow velocity. Now, this relation holds for all isentropic turning, either compression or expansion. However, the relation changes for finite isentropic compression or finite compression, which is compression by shock. The usual sign convention for the angle theta is that theta is positive for compressive turn and is negative for expansive turn. Now, integrating this relation, we find minus theta plus k is or k is the constant of integration. Now, to evaluate this integral, we write flow velocity w as speed of sound multiplied by the Mach number, and which gives us d w by w equal to d m by m plus d a by a. Now, to evaluate this in terms of the Mach number m, we use a naught square by a square equal to 1 plus gamma minus 1 by 2 into m square. This gives us d a by a, and substituting this relationship here, we obtain d w by w as d m by m into 1 by 1 plus gamma minus 1 by 2 m square, and hence we have and this integration is a function of Mach number, we will write as this. Now, that integral can be evaluated to be this root over gamma plus 1 by gamma minus 1 into inverse tangent of root over gamma minus 1 by gamma plus 1 into m square minus 1 minus tangent inverse tangent of root over m square minus 1. This function is popularly known as Prandtl-Meyer function. And as you can see, have a unique value for a particular value of Mach number, or we can say that for each Mach number there is an associated value of Prandtl-Meyer function nu. The constraint of integration in this relationship the constant of this integration, that is k, is chosen such that the Prandtl-Meyer function nu becomes 0 when m is 1. And this gives this relation essentially holds for both expansion and compression turn if the turn is isentropic. That means, it holds for smooth compressive turn and all expansive turn, and you must remember that this relation does not hold for compressive turn through a sharp corner, for which we have to use the shock relations. In a compression turn, the Mach number decreases, and so is nu decreases, while in an expansion turn Mach number increases and nu also increases. You have seen that a supersonic Mach number is always associated with a unique value or definite value of the function nu. Now, nu is a continuously increasing function as m increases from 1 to infinity, that is, as m increases from 1 to infinity, nu increases from 0 to say nu max, and each m has a definite nu. We can also see that the value of nu max, is as m approaches infinity, the function becomes pi by 2, that is equal to 2.27685 radian or 130.454 degree if gamma equal to 1.4. We can also see from the relationship that as nu decreases, as m decreases, nu also decreases. So, in a compressive turn, nu decreases and expansion turn nu increases. And in each case the decrease or increase in nu is equal to the amount of flow deflection or theta. So, if we know the initial value of nu, that is knowing the initial Mach number m 1, we can find the initial value of nu 1. Then the value of nu for a given amount of turn or given value of theta can be obtained, and this will give us the corresponding m 2, that is before turn we have known m 1, this gives us nu 1, after turn nu 2 is known, which will be or decrease or increase by the amount of absolute value of the flow turning. And this will give us m 2. And knowing m 1 and m 2, using isentropic relationship, all flow parameters can be obtained. So, flow parameters can be obtained from isentropic relationship. We can so here say that let us consider a compressive turn we have here m 1 and nu 1 is known. M2 is known, nu can be found by the amount of turn. Similarly, if we consider an expansive turn, and this nu 2 in this case can be found as mu 1 minus so from nu 2 will be getting M 2 and from known M 2 all flow parameters using isentropic relation. And since in these cases we are considering only isentropic turns P0 and P0 and T0, that is total pressure and total temperature remain constant. Now, the special feature of this isentropic compression and isentropic expansion is that the waves are in this case straight Mach waves with constant condition on each one and by the simple relationship between the flow direction and Prandtl-Meyer function. These are the special features of isentropic compression and expansion, that is, they are distinguished by constant or straight Mach lines or Mach waves with constant conditions on each one of them, and the properties are obtained or computed using the simple relationship between flow deflection and Prandtl-Meyer function. Now, these Mach waves, as you have already discussed, the Mach waves belongs to one of the two families, that is either plus or minus, depending on whether the wall that produces that Mach wave is to the left or right of the flow. In a region where two simple waves of opposite family interact with each other, the flow is of course not simple. In the non-simple region, the relationship between nu and theta is not the simple one given by nu equal to nu 1 plus minus theta. So, if we can show it, we can show it by a simple let us say consider the flow in a duct. So, these are simple web of belongs to this family as they originate from the wall and moves towards left in the flow. Similarly, these are simple waves of plus family or right running family. Similarly, these are left running family, and these are of course where two sets of Mach waves or Mach lines interact. These are all non-simple region. And the relationship nu equal to nu 1 holds in simple region only. Now, with this we will look into the possibility of reflection and intersection of oblique shocks. We have seen that the simple waves they intersect. So, similarly, these two oblique shock of finite strength can also intersect and they also can reflect, and we will see what happened when they reflect. So, first of all let us consider the reflection of an oblique shock from a solid wall. Reflection and intersection of of course, we will consider on some simple situation, while reflection and intersection of oblique shock is quite a vast subject and may be quite complex. But first of all let us consider a simple case where let us say we have a solid wall and let us see what happens to a shock which is being created somewhere. Maybe let us say that we have a wedge here, or let us forget about this, and a shock is created from here, and this shock as comes it hits this wall. Now, we will see what happened to this shock. We have seen that as flow crosses this shock, it turns by an angle equal to the semi-vertex angle of this wedge and become parallel to this wall. That is, a flow which crosses this shock turns clockwise in this case by an angle theta. Now, the wall here sets that the flow here must be parallel to the wall. The implicit flow boundary condition near a flat wall, that the flow must be parallel to that flat wall. Now, this shock turns the flow clockwise by an amount theta. Obviously, then this flow must again turn by an amount of theta in the anticlockwise direction, so that it becomes parallel to the wall, and this can be achieved if we have another shock another shock which turns this flow by an anticlockwise theta. So, we see that this shock which was coming here and hits the wall is reflected back again as an oblique shock, but which produces an anticlockwise turn of the same amount. So, this is here the incident shock and this is the reflected shock. This shock turns the flow clockwise by say theta. Similarly, the reflected shock turns the flow anticlockwise by theta. And it shows that the reflected shock is of opposite family. So, we come to the first law of or first rule of shock reflection, that is, when a shock is incident on a solid wall, it reflects back as an oblique shock of opposite family and turns the flow in opposite direction from the incident shock, but by the same amount, that is, the reflected shock in terms of flow turning has same strength. However, you can see that even though the deflection produced by these two shock are same, that is, deflection is same, deflection is equal in magnitude, but the pressure ratios are not. Now, the strength of the reflection is given by the product of strength of each. The strength of each, which can be written as the strength of reflection is written as P 3 by P 1 and this will be written as P 3 by P 2 into P 2 by P 1. This is, let us say, M 1, M 2, M 3, P 1, P 2, P 3. Now, why this P 3 by P 2 and P 2 by P 1 are not same? You can see that the two shocks have same value of theta. However, this M 2 is smaller than M 1. Consequently, the two pressure ratios are also not equal. We can also see that the wave angle beta, the two wave angles are also not equal. The two wave angles are also not equal. Two wave angles are also not equal. And this shows that angle of incidence and angle of reflection is not equal. Angle of incidence not equal to angle of reflection. Or shock reflection is not specular. Is not specular. A reflection is called specular when the angle of incidence is same as the angle of reflection, and since we see that in a shock reflection this angle of incidence and angle of reflection are not same, the shock reflection is not specular. The pressure change, we can see that on the wall pressure distribution on the wall, the pressure is uniform until the point of contact where a pressure rises. P ahead and P behind. However, on a streamline on a streamline, this is on the wall, on a streamline little away from the wall, we have the pressure ratio P 1, P 2, P 3. So, what you see here that when an oblique shock is incident upon a solid wall, it reflects back. However, it reflects back as an oblique shock of different family, and this, as you can very easily see from the consideration of the boundary condition, which states that the flow must be parallel to the flat surface, or the boundary condition of 0 normal flow or tangential flow, as usually we call it. So, according to that boundary condition, the flow must remain parallel to this solid surface, and to satisfy this requirement, an incident shock must reflect as again an oblique shock of opposite family. However, both will produce a turn of equal amount. One will produce say a clockwise turn, then the other will produce anti-clockwise turn, or vice versa. However, even though this flow deflection is same, the pressure ratios of each of these shock, that is incident shock and reflected shock, are not same, since the shock occurs at different Mach number. The incident shock occurs at a Mach number m 1 and the reflected shock occurs at a Mach number of m 2. We also, the strength of the reflection is given by the product of these individual shock, that is incident shock and reflected shock. We also see that since the pressure ratios are, since the shock occurs at different Mach number with same amount of deflection, consequently the two wave angles are also usually not equal, and hence the incidence angle and reflected angle are also not same. That is, the shock reflection is usually not specular. Now, we will see that what happens when two shock intersect. In this earlier example of reflection, shock reflection, the wall which can be thought of as a streamline and an inviscid flow. So, if we assume that to be the central streamline of the symmetric flow in the intersection of two shocks of equal strength, but of opposite families. That is, say that wall in the earlier case, let us consider that to be just a central streamline, and we can see that this situation has come because of say here we see that two shock have intersected here. However, as you can see that these two shocks are of opposite family. So, in this case we have two intersecting shocks are of opposite family. One belongs to the plus family, or the other belongs to the negative minus family, or there is one is left running, the other is right running shock, and of course, the deflection that they produce are of different sense. One produces a clockwise turn, the other produces an anti-clockwise turn. Now, if these two shocks are of same strength, see the shocks pass through. The shocks pass through, that is, this shock will continue to move this direction and this shock will continue along this direction. However, they bend slightly. This we can see, let us say that if we consider these two of same strength, consider equal strength. That is, that this flow has turned the, this shock has turned the flow by theta in the counterclockwise direction, and this flow, this shock has turned the flow by theta in the clockwise direction. And considering that if the Mach number here was m1, then after the shock this becomes m2. Similarly, here also this is m1, and since we are considering this shock to be of same strength, this is also m2. Now, you see that in this part of the flow, the Mach number ahead of this shock is m2, which is smaller than m1. Consequently, for the same amount of flow deflection, there is same amount of flow deflection of theta at a Mach number of m2, the wave angle will be slightly higher. Consequently, this, instead of following this path, it will now move like this. It will bend slightly to that side. And this shock of course turns the flow in the opposite direction by again same amount, so that it will become parallel to what it was coming earlier. Similarly, same logic applies here also, and consequently the shock here also and all the flow parameters at anywhere in this configuration can be determined using the shock relations. And so, knowing the value of theta here, we can find out what would be the beta here, and then we can find out what are the pressure, density, temperature in this part of the flow. And again, knowing that Mach number here and the flow deflection by this shock, we can find out what would be the wave angle for this shock, and we can again construct this shock. And finally, again using those shock relations, we can find out the properties here. the shocks pass through, but that is this shock pass through this shock. However, because of this passing through, while passing through it bends towards this interacting shock, and this happens since M2 is smaller than M1. This implies higher wave angle for same theta. In case these two shocks are of not equal strength, what happen in this case when the two shocks are of unequal strength? Let us say that this is the first shock and this is the other shock coming let us consider one particular flow streamline here. M1. Now, let us say this turns the flow by an amount theta 1 prime, while it turns the flow by theta prime, and the Mach number here is M2 prime, here it is M2. Since the two shocks are of unequal strength, M2 and M2 prime will also be different. and the downstream Mach number will be smaller for the stronger shock case. Now, these two shocks will of course pass through, but as you have seen earlier they will bend, because now let us see, through this shock the flow will turn by theta 1 prime in the opposite direction. Now, when theta 1 prime and theta prime they are same, then this flow will be of course parallel to this, but since in this case they are of unequal strength, they will no longer be parallel to the upstream flow direction. Let us say that theta 1 prime is higher than theta prime, that is, this shock is stronger. Consequently, this flow instead of becoming parallel will now move slightly to that direction. And so, we see that this interaction has produced a net amount of turning, and in this case towards the upper side, and similarly for a streamline which is now crossing through this will simply undergo a turn by this. This streamline is known as a dividing streamline or strip line. This is called slip stream, because there is some essential differences between the stream enclosed in this side and enclosed in that side, which you can very clearly see that. Consider this particular streamline which is crossing these two amount of shock. Now, as you have assumed in this case, this shock is stronger than this shock is stronger than this shock. Consequently, the entropy rise across this shock is higher than entropy rise across this shock. However, we can see that both the streamline, this as well as this streamline, both of them are causing the same two shock, However, the total entropy change that will be experienced by these two streamlines are not same. The reason is that here in this lower half, the undisturbed stream is experiencing the stronger shock at a higher Mach number, and the lower shock relatively weaker shock at a lower Mach number. While in this part the undisturbed stream is experiencing the relatively weaker shock at a higher Mach number, but the little stronger shock at less Mach number. Consequently, the entropy change across these two shocks are not same. Hence, the entropy in this part and entropy in this part of the flow are different. Since entropy in two part similarly, the density change or temperature change experienced by the flow crossing these sides of these two shocks are different from the density, temperature or velocity changes experienced by the flow in this side of the shocks. Consequently, in these two streams, all the flow parameters except pressure and flow direction they are different. That is, if we consider these, so we have density, temperature, velocity, entropy are different. However, pressure is same, in the two regions, and also flow direction. So, until now we have considered interaction of shock waves of same family. Next, we will consider interaction of waves of same family. Earlier, we have considered interaction of waves of different family, and next we will consider interaction of waves of same family in our next lecture.